60 gauge theory, will describe some, at least in the perturbatory regime, will describe some region near the origin of the Coulomb branch. But here, from this string theory point of view, I haven't said so far what a string theory is. Its effective coupling is controlled by 1 over W boson mass. So the string coupling is, the effective string coupling is going to be weak in this other region. That is far away from the origin on the Coulomb branch. This is where the double scaled string theory is weakly coupled. So, no, as usual, these are equal enough in overlapping regimes, but well, if you, the perturbatory theories are not in overlapping regimes, but that's usually why duality is actually useful, to say something non-trivial. So, how does one figure out what the string theory actually is? Well, that's in principle straightforward. Yes.
Is that the region where supereminence is free?
No, I mean, wait.
The decoupling, the double scaling. So I mean, you have infinite W mass boson, right? So you just have a bunch of U1.
The Yang-Mills theory is. Well, I'm going to be looking at the Yang-Mills theory has a dimensional coupling, and so if you depends on wait, where you're asking on the Coulomb branch. If I'm sitting at the origin, the Yang-Mills theory has dimensional coupling at energy scale high compared to that scale, which is same as the string scale. Theory is going to be strongly coupled. At energy low compared to that, it's going to be weakly coupled. If you move off the origin on the Coulomb branch, then you can have if you focus on the massless degree of freedom, you'll interact with the loops of W bosons. Then yes, if you have W boson mass very large compared to that scale, you might expect the theory to be weakly interacting. It is true that the abelian, the massless abelian gauge boson degree of freedom, if you are far away on the Coulomb branch, is going to be weakly interacting with the coupling, effective coupling controlled by this G effective, which is 1 over W boson mass in the units set by the Yang-Mills coupling. Okay, so now to figure out what that string background is, that's in principle straightforward. You just need to look at the superquadratic solution carefully and you know, and take the decoupling limit. Just follow this. And this was in fact.
Sorry, the dimensionless combination of G Yang-Mills and NW is G Yang-Mills times NW.
Yes, so I should put G Yang-Mills here, I guess. Yeah.
Right. So if NW is becoming large, that's G Yang-Mills times NW becoming large.
That's correct.
So when you go far away in Coulomb branch, it looks like the effective coupling from the Yang-Mills point of view is becoming larger.
That's right. So it's not obvious. I mean, the thing is, in the Yang-Mills theory description, I mean, there can be all kinds of high-dimensional operators who become important when the scalar VEV is large. And if you don't know what they are, you could worry that the Yang-Mills description completely breaks down. So it's not obvious that the Yang-Mills theory has anything to say about double scalar string theory. It's not obvious that if you compute something on the side, anything to do with computation, perturbatory computation in Yang-Mills theory. That is indeed true.
Right. So, but if G Yang-Mills times NW is small, then you should trust the Yang-Mills.
Yes. Yes. That's exactly right. But of course, I mean, the reason that you might expect that the masses degree of freedom are still weakly interacting is because the W boson mass is large, and these things interact through loops of W boson.
I understand.
But okay. So in a nice paper by Spetsos, 98, we worked out the take this kind of superquadratic solution and just look at the decoupling limit and perform various kind of T dualities and to see what it looks like in the horizon limit and whether there's some you can come up with some nice worksheet description. If you can, then that worksheet description would allow you to formulate string theory in this background, which a priori would be something stringy, but nonetheless perturbative in GS. If I call this angle phi and call this angle psi, then it turns out that at least if the number of five rank is large, by the way, ultimately in this whole discussion, so we're talking about SUK gauge theory. K is going to be kept finite. I'm going to look at cases k equals 2, 3, 4, 5, and there's no large n limit here. But a priori here for the supergravity description to be valid, you need k to be large. But once you learn what that appropriate stringy description of the near horizon geometry is, you can then conjecture that could be exactly true for even finite k and ask if it makes sense, and it seems that that does make sense. At least, for k much greater than 1 from a supergravity point of view, you take the near horizon limit on this double-scaled geometry, and then t-dualize along this phi angle. You do that. And then you discover some very nice geometry. Turns out so this you have to do some computation. It was done in this paper. And it was so the transverse geometry, the transverse four-dimensional geometry, becomes the following. So there's some radius. This radius, this r squared is just k alpha prime, as seen before, times there's some radial coordinate d rho squared plus cup squared rho d phi tilde squared over k plus d psi squared plus d theta squared plus tan squared theta d phi tilde squared over k squared. Here the psi is the same as this angle coordinate here. The rho and theta come from some radial combination of the radial coordinates, and phi tilde is the t-dualized coordinate of this phi. There's going to be some varying dilaton in the background. So phi goes like g effective squared over k times 1 over cosine squared theta sine squared rho. And here you see very explicitly that this g effective indeed will turn out to be the string coupling for this background. Okay, so what is this? What is this thing? Now, this is a pure geometry. There's no H flux anymore. And if you look at, let's first look at this guy here. Well, if you look at this guy, this it's kind of weird. This looks like some kind of disk, but the distance to the bound, so theta ranges from, let's say, between 0 and pi over 2. The boundary of this disk is a finite distance, but nonetheless the circumference blows up. So this is usually called the Bell, the Bell geometry. Well, it's not a pure geometry because there's also very dilaton. The string coupling blows up toward the boundary of that. It's well known that this is described by SU2 mod U1 coset theory from the worksheet CFT point of view. You can see that by the gauge W0 model construction, which
why shouldn't I be worried that the dilaton blows up?
Why shouldn't?
Yes.
Well, that's purely artificial. Well, that's due to the limitation of this classical description, and we know an exact worksheet description in terms of the coset, and the dilaton is perfectly fine. So the way that comes about is that if you gauge the SU-W0 model and integrate the gauge field, you get the natural dilaton from the function determinant. Since you know that how to solve that CFT, you don't worry about this.
Actually, the blowing up was just because of the size of the circle, because of t-duality on a very small circle.
Yeah. on the other hand, by the way, okay, let me leave it like that. And
so before you TDU-lize, there was no blow up of these strict coupling.
let me see. That's probably true. Yeah,
Okay, yeah.
that's probably true. Yeah. Good. Now this other thing here. Okay, what this geometry looks like. So this again is kind of a circle of varying size. It looks like this, and yeah, I guess. Sorry, this circle goes to constant size at large rho. Constant size large rho, and it follows up at as rho goes to 0. It's the rho direction. Think of that as the sine direction division. So this is called a trumpet geometry, which is basically related to the cigar by T duality. Usually a cigar is the more common terminology. One does not talk about the trumpet too often, but if you do this, you get the trumpet geometry. The data is also varying, and this is described by SL2 level K mod U1 coset CFT. I was going to review the gauged WZ model construction that goes from SL2 to the geometry, but I think I won't have time for that because I'm going much slower than I had planned. Let me just say that if you, alternatively, if you T-dualize psi direction instead, then you will actually get cigar times the kind of a T-dualed version of the bell geometry. So this is the cigar and something called T-bell, which is basically T-dualized version of that. Anyway, from the worksheet CFT point of view, it makes no difference. But I want to point out this division by K. So actually, the worksheet CFT is not just a product CFT of this SL2 mod U1 with SU2 mod U1, but rather it's a orbifold on top of that. So the upshot of this discussion is that double-scaled Leo string theory is described on the worksheet by string theory R1,5 type 2 or type 2A or type 2B. I have to keep remember that we have done T-duality, but anyway, times SL2 level K. This is going to be a supersymmetric SL2, which I will review in a moment. Times SU2 level K mod U1 mod overall ZK. So each of these cosets is going to have a ZK symmetry, and you further orbifold this by ZK. In fact, let me explain this ZK orbifolds a bit. This is actually kind of important. So, if you started with the in the original, before the actual strongly coupled Leo string theory, which is described by the linear dilaton times S3, which can be, from the worksheet point of view, is the supersymmetric SU2, the equals 1 SU2 W0 model with level K. So this is from the worksheet point of view, there's also R1,5 comes along with, right? This is the equals 1 W0 model. 1,1 W0 model. So this consists of bosonic SU2 at level K minus 2 plus 3 free fermions. Since I'm actually running quite short in time, despite having 3 hours, I fear that I have to skip some things. The one assertion is going to be that this SUW model is actually a level CFT is equivalent to U1 times the coset SU2K mod U1 mod ZK. So these two are the same CFT. This is non-trivial. I don't think this holds for the bosonic case. It only holds for the supersymmetric theory. And in fact, this coset construction, which, as you usually do, you take so here the SU current algebra, the currents are constructed from the currents of the bosonic SU2 at level k minus 2, together with the SU current constructed out of three fermions. You are supposed to gauge the so the J3 component of the SU2 current, and also the fermion partner of that, so as to preserve supersymmetry. But in fact, after you do the coset construction, this thing has n equals 2. This is n equals 2 superconformal theory. So here, then you're left with, so this whole thing, you can express this as R phi times this U1 is some free boson, compact boson, times this and mod ZK. The ZK only acts on this U1 by rotation. So this is the phi, I think like I mentioned, phi direction. And what this cigar geometry does is that what this deformation does is that it caps off the cigar and replaces R phi times U1 to the SL2 level K mod U1. The funny thing is that it turns out if you do this whole thing together has n equals 4. This is n equals 4 superconformal theory. You can verify that by checking the center charge. For example, SL2 at level K mod U1, center charge is so the SL2 mod U1, the bosonic part of this is SL2 at level K plus 2, just like how the bosonic part of the supersymmetric SU2 is level K minus 2. So the center charge will be of this internal part of the CFT would be 3 times K plus 2 over K for the SL2, and minus, well, it will be this plus the 3 fermions, 3 halves. Then we multiply U1, you are throwing out a U1 current together with a fermion partner, so actually minus 3 halves. That's a center charge of this SL2 mod U1 CFT. And then you have this 3 times K minus 2 over K minus 2 plus 2, which is center charge of the bosonic W0 model. And again, add 3 fermions. But when you do the coset, you're going to throw out center charge 3 halves. And of course, the result of this is equal to 6, as must be for any n equals 4 superconformal theory. That's so center charge will be multiple of 6. Okay. So I guess I won't have time to explain why, from the CFT point of view, why you have to do this overfold here. But anyway, it's something that can be derived from the gravity point of view. Now let me discuss the spectrum of the strings here. So in this, so I claim that SL2 mod U1 CFT describes that cigar geometry, where the cigar is basically this cup replaced by the 10, with some appropriate dilaton profile along the radial direction of the cigar. I won't have time to explain this, but one can show that this is described by the SL2 model U1 coset by starting with SL2 WZW model and gauge it into real gauge field, some gauge fixing into real gauge field, and you discover the signal model on this geometry with varying dilaton profile. The varying dilaton come from the one loop determinant as integrated gauge field. Anyway, this is it's a famous story. And on this, to ask what are the string modes on this space, there are some, you can make some wave packet of strings that propagate down the cigar. So these would be some modes with real momentum in this linear dilaton direction. So this gives rise to a continuum of delta function normalizable states, as you would for normalizable states. And then there turns out to be a set of discrete set of normalizable states living at tip of the cigar, which in particular are going to contain the massless modes that precisely agree with the massless degree of freedom for the six-dimensional super Yang-Mills theory on in the type 2 ideal string theory case on this Coulomb branch. So if you take that 1.1 super Yang-Mills theory on the Coulomb branch, you get this set of k-1 abelian gauge multiplets, and they will correspond to some particular, will be described by some particular vertex operator that are localized, normalizable, localized at the tip of the cigar. In order to describe this explicitly, oh, by the way, before that, I think I should, maybe I don't have time to say this. There's some connection to strings in ADS3. In fact, these are closely related, and these discrete states at the tip of the cigar, and this continuum of the states that have real momentum that propagates down the cigar are related to these short and long strings in ADS3. But that's it. I won't have time to explain.
So you can see that these states at the tip have a U1 gauge invariance associated with them.
U1 gauge invariance.
Have a U1 to the power k.
I mean, I will write down explicitly what those vertex operators are. But unfortunately, now when you're okay. But those are spelled out explicitly in our paper.
But what I mean is that these vertex operators will only be defined up to a gauge structure. There will be null states. So the gauge there.
Yes. Yeah, but that doesn't have. Well, okay. Yeah, but that's something very generic. Whenever you have the massless vector bosons.
Right. Okay. So I should just say that there were vectors.
Yeah. Well, the vector boson and scalars and the fermions.
Right.
In fact, in this description, the vector boson are going to come from the Ramon sector, and the scalars come from NS sector.
I see. And the current algebra of these, so there will be sort of currents on the world sheet, like J mu's.
Yes.
And the current algebra will be that of U1 to the power k.
No, the currents are going to be in the R1,5 direction, so that doesn't have much to do with this. I mean, this is just an internal vertex operator, and then you have to combine this with R1,5. That the vector boson index is in the R1,5 direction, so it's just the usual story.
But in the end, you get k gauge bosons in
K-1, yes.
K-1 gauge bosons. These K-1 gauge bosons are associated with vertex operators.
Yes.
And the vertex operators, have, I mean, you see that as U1 to the power k is what I say, not SUK.
Oh yeah, absolutely. Okay. At this point, I need to. So the next thing I want to explain is the explicit construction of these vertex operators. So if we have these vertex operators, we'll be able to calculate their scattering amplitudes. So the way you would construct these vertex operators is fairly standard through this coset construction. You will start with SL2 primary, which will be labeled by some SL2 spin. Let me see. I'm going a little bit out of order because I have to skip a bunch of stuff. Anyway, so if you start with phi, so SL2, current algebra primary, will be labeled by some vertex operator phi, j, and bar, where this j is the SL2 spin determined by the Casimir, SL2 Casimir, and m and bar are the spin with respect to some J3 generator of SL2. I think I should write something more explicit here. So, there will be some SL2 currents, called J plus minus and J3. The J3 will be bosonized to, so there's left on the right, the J3 will be bosonized to some boson X. Now, you can write this in the form as you'll factor out some, the bosons, you refer them, so some I square root 2 over K, some normalization n X, and for the left mover, and then you have some e to the I square root 2 over K, and bar X, the right mover. And whatever that's left over, so this would saturate the U1 charge of this SL2 primary, so whatever that's left over, I call it V, J, and bar, that would be identified with a primary of the coset model. So this will be the primary with respect to some kind of parafermion algebra, which you get by doing a similar thing to the SL2 current here. You can take SL2 current, J plus J minus, also factor out the corresponding exponential operator just involving the bosonization of the J3 current, and what's left over is going to be some set of parafermion operators. These things would have conformal weight, say H equals to minus J plus 1 over K for this phi, J, and bar, as usual for the square tensor. And for this V, you're factoring those out, and the result of that turned out to be just the m squared and over K on the left, and bar squared over K on the right. This is not the most general construction for primary operators in the coset theory. There are other primaries you get by multiplying this by some operator controlled out of the fermions in the theory, which will be some descendant from the mother theory point of view, but nonetheless, if you factor out this U1 part, you can obtain some primaries in the coset theory, which are essentially related to this by spectral flow. As you remember, this are equals to superconformal theories. So there's a spectral flow operator. Now, the question is, what is the value of J? In the SU2 case, that was well known. J takes value half integers and go up to K over 2 for SU2 at level K. Here, it's a bit funny. So in order for this component dimension to be real, you need J to be dimension dimension either in -1/2 plus a purely imaginary number, which would, so this will correspond to these continuum of the states that describe the strings that propagate down the cigar.